Our next talk is by Anurag, Mendhekar, and Daniel P. Friedman. So a lot of people here are students of people who are currently teaching Racket and work on Racket. But today I learned that there's someone here who's the teacher of someone who works on Racket. It's Matthias's advisor, Daniel, who is one of the speakers here. And Anurag is another student of Daniel's as well. They will be telling us about Malt, which is a Racket framework for deep learning that is intended to restore Lisp and Racket's rightful place as the main language for artificial intelligence. So let's hear about it. Thank you.
Thank you, Sid. So before I jump into this talk, I really want everybody to give a round of applause for Dan Friedman.
What did you do now?
Well, he managed to convince me that we needed to write a little book on artificial intelligence. So, yes, we owe that to him. This is the book. It's called The Little Learner, and its subtitle is A Straight Line to Deep Learning. Now, Dan asked me to sort of remind everybody that this book owes its existence to Matthias Verleisen, because Matthias was the first person to take the ideas from the Little Lisper, which was 1976, and then bring that into the modern age with scheme and everything else. So, a little bit earlier, okay. 71? 71, yes. Okay, so thank you, Matthias. Anyway, so this book was written with a very sort of unique perspective. And, I entered this field about a decade ago. And just, if you've studied artificial intelligence in its modern form, the mathematical background that you need consists of linear algebra, vector calculus, probability and statistics, signal processing, just the body of knowledge of prerequisites that you need in order to learn how a basic neural network works was just incredibly high. And so the idea behind this book is to try to remove that baggage from learning this space. So that word up there is a word written in Hindi. It's pronounced funde. Okay, now funde is sort of this uniquely Indian phrase. If you go through higher education in India, there's like, at the end of the semester you have an exam and that's all it is, and you basically work through the semester to clear the final exam. Right? There's two ways to do it. One is you can memorize your way through the semester and like, okay, I'm done. At the end of it, I've cleared the exam. The other way to do it is to truly understand what the subject is about and sort of axiomatically figure out what the subject is. And the students who do that are said to have very clear funde. Now, funde is short for fundamentals, okay? But funde has now become sort of this colloquial usage all across India. And my mother will ask me, what is the funda of this toaster, so that she can actually operate it? So it is sort of this philosophy of the pedagogy of first principles, that you actually understand the subject from the bottom up, right? And that's what we've tried to do in this book, right? And sort of a great example of this. So Darshal and Yafei, who are two graduate students at IU, they actually offered a class based on the Little Learner, I think this past summer, was it? Yeah, this past summer. And at the end of the class, There were 10 students in the class. At the end of the class, they did an evaluation. And I asked him yesterday, how did the evaluation go? He said, we got 2 responses. One was very good. The other one wasn't so good. So I was sort of curious, okay, why was it not good? He said it was too simple. It was too easy. The class was too easy. And I'm sitting here thinking, we've just taught you linear algebra, vector calculus, probability and statistics, and signal processing, and we've taught you how to build a very complicated neural network based out of all of this. And his only complaint is it's too simple. So I took that as an anecdotal evidence that the approach actually worked. So, this talk, of course, is about the code in Racket, scheme mostly, actually. But we deliver it as a package in Racket. Well, one of the critical requirements for us was that it be dead simple. And literally, something that only relies on your basic stuff, right? And the idea was that you should be able to write it naturally in a functional style, because of course it's functional style. But it's minimalist, it's very easy to understand. And like all other little books, it pretty much includes everything from soup to nuts. So we'll talk about all the different things that you need to have before you can actually run a neural net, but you can build it all by yourself if you wanted to. Okay. So let me give you a few examples here. Oh, before that. So obviously, when you're writing a little book, you're focused on the first 2 things. It has to be natural, it has to be minimal. But you're not really thinking about, is it scalable? Is it going to run big programs? Am I going to be able to use this in real life? And obviously, this has the same issue, but we're trying to address that. Okay. So what do I mean by natural, right? Now, if you've built neural networks before, you know that one of the things that you have to do is determine a set of parameters that will optimize a certain loss function. Okay, that's sort of the bread and butter of pretty much all machine learning. They just do it in different ways. So you want to be able to write a loss function in sort of the obvious way. And the one I picked here is sort of the what's called L2 loss, the sum of squared errors. So literally, you can see the word sum, you can see the word square, you can see the difference between what's predicted and what's actual. And theta over there is the set of parameters that you want to optimize. Okay. Now, this code directly mirrors the underlying math. So when you look at the SSE definition, there'll be a sigma, x, y minus, x whole squared. This code also works on scalars, it works on vectors, it works on tensors of any order, and is completely automatically differentiable. So you never have to worry about it. Okay, and why is that important? Because when you're trying to optimize the set of parameters, which in this case is theta, you typically use a gradient descent algorithm. So a gradient descent algorithm determines the gradient at each step and then uses the gradient to refine the estimate of whatever it is that you want. So, so it's very natural, you could say this. Okay? And then you need a gradient. Well, this is how you get gradients in math. This is how you get gradients in Malt. There is no artifice, there is no fuss. You just say what you want. The second form there, nabla super 1, sort of points out that it's the first order gradient. The system we have actually can do higher order gradients, but that's sort of secret. We don't actually talk about it. There's a little bit of work you have to do to make it do that, though. And then here's an example of how it can all come together in this little function up here that does gradient descent optimization of pretty much any objective function that is written, using our framework. The inflate, deflate, and update, the first three arguments there are higher order functions that actually allow us to model all of these different types of gradient descent algorithms. And just that simple driver there with the right arguments can actually model these and possibly many others that, forms of gradient descent that are used popularly. The book itself covers, I think, the top line over there. Which then brings us to the actual objective functions that we're trying to optimize. Now, a typical neural net framework will have this complicated TensorFlow graph or some nonsense like that you have to build. For us, though, you write the function. This is a standard neuron. It's called ReLU, which is rectification of a linear transformation of a tensor with a parameter set theta. And that there is a way to generate an arbitrarily deep neural network of dense layers. Right? Now, one of the sort of implications of doing things this way is everybody is probably familiar with this model of neural networks where you have these circles. They draw these circles and the arrows between the circles. In our book, there are no circles. Because what we can do actually is describe things that we want to say with very simple lambda expressions. Right? And so what this little thing on the side, this KRLU, you can use it to model encoders, decoders, autoencoders. You use multiple instances of this to create very, very complicated neural networks. Right? So the end result is that we're using all of this power of Scheme and Racket to have this really expressive framework that allows you to do all of these different things. So, how does it actually work? What we have is a minimalist core. And that core consists of three parts. An implementation of tensors. Now, I'll talk a little bit about what tensors actually means in case you haven't heard the term before. There's automatic differentiation. And there are operators or primitives, things like sum and square that we saw in the beginning over there. Okay. And everything that has to do with deep learning is actually user-level code. And it is pretty much representation independent. So you write it once and you forget about it. Almost. But that representation independence, what it does is it allows us to actually think about the implementation of Malt on this spectrum of things that we're concerned about. So the first implementation up there is what we call the learner implementation. And it's primarily pedagogical. It is designed to be very simple, easy to understand. And then as you sort of get to more industrial strength, remember how I talked about scalability? This is the spectrum that gets you to that scale that we want. We have two other implementations in the book. One is called nested and the other is called flat, which are actually more efficient versions of the same thing that we have in Learner. And we describe how they should be built in the appendix of the book. The the key thing about all of these implementations is that they are designed to be CPU only. So they only run on a single CPU in standard Racket. The next level that we need to get to be truly scalable is to start incorporating GPUs into it. And even going beyond that is we need to get into sort of the hardware level of things and have dynamically configurable hardware to be able to run these things. So the reason they're in red is we're still not there yet. The work's in progress. We're working on an implementation for GPUs right now, and Darshil is working hard on it, and hopefully we can convince him to work on the rest of it with the FPGAs. So let me talk a little bit about these tensors, right? So tensors, by definition, have this very sort of elegant recursive structure. You don't have to read it, don't worry, and I'm not going to walk you through it. But just think of it as an n-dimensional array of a certain scalar type. Okay, and that's all that you get presented with it. There's iteration operators that will help you navigate tensors, and I'll talk about those in a minute as well. In the learner implementation, we use standard scheme vectors and nested vectors, which is what gives you the n-dimensionality. And the scalars are what are called dual numbers. I have them in quotation marks, and I'll talk about them in a minute. When you get to the next level of implementation, it's still the same thing. You have nested scheme vectors, but the scalars are actually numbers. They're real numbers. Yeah, they're not duals anymore. In the flat tensor, it's the same thing, but instead of nesting the vectors, you sort of deal with this one big flat, sort of like the way C handles its memory. For these, the vectors really have to be represented in something that the machines understand. So you can pass them back and forth between the GPU or whatever associated hardware you have. So automatic differentiation. So unlike most other systems, our automatic differentiation runs entirely at compile time. Entirely at runtime, not at compile time. And what we do is we sort of, as we're computing the results in an operation or in a neural network, we are assembling this, what we call a link function, which is essentially a backpropagation function. We're constructing that, and then when we need to take a gradient, we just run that function that we just constructed. So in learner, they're basically your tensors can contain these pairs that consist of a real number and a function. So it ends up being fairly computationally intensive to run large tensors here. In nested and flat, what we do is instead of doing the links at a scalar level, we put them at a tensor level. So they move up one level of data aggregation, so that makes it much faster for the automatic differentiation to run. And then finally, for the OpenCL version, everything is just-in-time compiled into GPU code. So now you have the same functions that we just wrote, but now they're running on these very fast GPUs, and then you can sort of extend that to the hardware when we get to it. Operators, again, operators are sort of written in this style of using abstract iteration operators, which extend primitives into more sort of tensor-friendly operations. This is what allows us to use the L2 loss function as it is written without having to worry about the dimensions of the vectors or the tensors that it's getting. So we have a couple of operators. We call them extend1 and extend2. They're sort of like map. Think of them as a map that works on tensors. And one of the things that we also want to add eventually is a reduce operation. And I don't know if have you guys heard of a language called Futark? Somewhat esoteric, but Futark actually has map and reduce operations that directly map to GPUs. So it's a very GPU-friendly parallel programming language. So we're sort of taking inspiration from that and putting it into this framework here. Same thing in the learner implementation, the primitives are just scheme or racket. And in nested, again, it's a similar thing, but you're changing how the dual works a little bit. Finally, in OpenCL, you're using these map and reduce operators. You want to be able to algebraically optimize them, generate GPU code that is basically OpenCL code, and the primitives are defined in OpenCL. And then finally, or Verilog, if you go that way. So that sort of brings us to the way we're thinking about this, right? So Lisp used to have a killer app, right? Its killer app was AI, and AI really is the reason why we're assembled here today, because Lisp got so much money in the 80s to build the fast compilers, to build the Lisp machines, and all these fantastic innovations that we live with today sort of came from that sort of very fertile period of funding that Lisp went through. And then there was the AI winter, and everything just died, and here we are, a handful of people remaining who are still holding the flame. Unfortunately, in the meantime, someone stole our killer app. Poopy Python, as I call it. Poopy Python stole my killer app, and I want it back. All right, I want it back, but I want us to start thinking about how AI sort of should come back to the Lisp realm and to us again. But it's not an easy task. Right? There's a lot of work, there's a lot of progress that has been made in how AI is built today and how it gets deployed and how it gets trained, and so all of that work has gone in, and we're starting over there, far left. We're CPU only Malt implementation, and where the rest of the world is way ahead of us. Okay, so it's not easy to make that paradigm shift unless we're solving a real big problem that exists in today's systems. People aren't motivated to use a new tool unless it solves a big problem for them. So where is this big problem? The way I can see it, the biggest problem that we face is the planet. And what that means is energy consumption. All the AI systems that exist today, they run off of these massive GPU farms that are big, expensive, power-hungry, heat-generating monsters, right? And the only way and that's the big problem that the infrastructure has. And one of the reasons why I have been emphasizing the reconfigurable hardware as one of the target options is that that's the only thing that we can see on the near horizon that actually solves that problem. FPGAs can reduce power consumption by more than half. They can be faster than GPUs. The problem is nobody knows how to use them because the interfaces are complicated. You have to be a hardware engineer to define whatever it is you're doing. So on the other hand, a system like Malt starts with an abstraction that actually makes sense for the domain. So you can take that abstraction, and if you can find the ways that we all know how to do with the compilers that we've written and all of these nano passes, right? I would like my last nano pass to be, I'm just generating FPGA code, right? And if I can do that, then I suddenly have a huge advantage over what the existing systems are able to do. You can make dynamically configurable hardware that gets us where we want to be. In the middle, of course, there's real problems that need to get solved. So there's all these intermediate points that we need to build systems for. So in some ways, I'm here today mostly to recruit you guys to come work with me on this. It's exciting, it's fun, it's a whole new domain. And look, I've always believed that the Lisp community is the smartest people on the planet. So we need more of them. With that, I will turn it over to you guys for questions. I have, following Jeremy's lead, a bunch of books over here. Okay? I won't say how many. And I will give out a book for each question. So if it's a good question, okay? And I'll let, and Dan will be my judge for whether it's a good question or not. So if he gives me a thumbs up, you'll get a book.
Okay, just on a note, we are running a little behind. Should we push it 10 minutes past and eat into the coffee break? Is that okay?
Rotate. Do the coffee break now.
No, we'll do the other talk and then follow that up with a 20-minute coffee break instead of a 30-minute coffee break. I think that would be the easiest. Does that sound good? Okay, so we have another 5+ minutes for a question, so go ahead, yeah.
So this is say exciting talk. So I'm personally I'm not a practitioner of AI or machine learning stuff, but it seems what I heard of people around me, they're using this current pipeline with Python or something to build neural nets or something. They're pretty satisfied with them. They say, oh, this is just like playing Lego pieces, and actually they don't really need to know how the multivariate calculus or how the probability stuff they're doing.
Yeah, which is very unfortunate, yeah.
Kind of, so I wonder, so you give these so many good things about this framework, about Malt. We see this elegant, say, compositionality in this first principle stuff. Do you have some kind of examples in the current that shows the current framework, say in Python, is pretty ugly, nasty?
Oh, just look at any Python code. It looks like crap. I mean, the way that these systems are organized, I mean, Python is a very poor language to express most things, right? If it's more than a page of code, you can't handle it. So you look at even sort of PyTorch is considered one of the most elegant frameworks out there, but even PyTorch has a very complicated way of setting up backpropagators and and all of those things. So it's not, like I said, you pretty much any code that you take, I guarantee you that the code that's written in Malt that compares to that is a lot simpler, a lot cleaner, a lot easier to understand. So yeah, pretty much anything can be an example. The problem we have today at Malt is that we're not able to operate at the scale that Python is able to operate at today because they have had some years of development. And so they can do many more things than we can. Thumbs up? Here you go, man.
Go ahead, David.
So, so first off, thank you both very much for an excellent book, which I have one of already, and for a really fascinating talk. And my question is this: what could the people in this room do to be helpful? So,
those dots need to get filled. Okay, We need to improve the GPU support. We need to improve
So what concrete action could we take?
concrete action. Send me an email. Darshal has some ideas. There's a Malt repo, yeah. There's a Malt repository. Feel free to fork it, understand it, change it, however you want to do it. But send me an email saying you want to be part of this.
Okay.
And we will, we will sort of schedule things that need to get done. I would love help on that.
Brilliant. Thank you.
I'm sorry? You have a book already, you said? I do. Do you want another one? Thank you.
Hi. So I've had, great talk first, but I've had a lot of similar ideas regarding lowering Lisp to hardware. But I'm curious how many advanced constructs you use in Lisp, like continuations, in Malt, if at all.
We don't.
Okay.
So when you boil it down, the way neural networks work in general is that you pretty much have a straight line function. Right? Just think of it as just going from top to bottom without any loops. But then you run that whole thing millions of times.
Yeah.
Right? So it's a very easy context to optimize. There's no continuation, there's nothing, it's just plain data flow.
Okay.
And so you get to a point where you know what the data flow looks like, then you can compile the heck out of it, put it on an FPGA, and then just run it over different data portions of your data over and over again.
Okay. Do you have any ideas, tiny follow-up, on what the hardware would actually look like? Like a...
I have some ideas.
Okay.
So today there exists a mapping from OpenCL to FPGA. They do have that. But it's a clunky, complicated, very static kind of a process. You have to know exactly beforehand how you want to do it. It doesn't have this dynamic flavor that Lisp in general has, and especially the way we've done Malt. So I do have some ideas about, they're still half-baked. We need to get to a certain point before I can bake them some more.
Perfect. Thank you.
Thank you.
Okay, I think we're out of time, but Anurag will still be around, so you can certainly
Yes,
discuss
please.
further during the break. Let's give it up for Anurag. Thank you.
Thank you.